We're looking at continuous random variables as an extension away from discrete random variables, and you're going to use continuous random variables in situations where you just aren't able to count up things. You know, in our discrete random variables, we've had values for x of like 0, 1, 2, 3, 4, 5. All the probability is piled up on those numbers. There's nothing in between. So when I ask what's the probability that x equals 2.5, well, there's no x value for 2.5, so that's just 0. All right, but there are times if you're measuring people running in a race, or if you're trying to determine how tall people are, then that could be any time or any height. So not just whole numbers. And so you're not going to be able to put all these numbers on a probability distribution like we did for discrete, like in a table. There's just no way. There's just too many of them. So this is for those kind of situations. So a continuous random variable x takes all values in an interval of numbers. So just if you have two numbers, there will always be a number in between them. So the numbers just go on and on and on indefinitely. And like I said, you can't summarize those things in a table. So you're going to have to go to plan B, which is to use a density curve. And most of the kids remembered what the main feature of a density curve is. It's a geometric shape underneath which the area is 1. And if these things do have an area of 1, they're perfect for chopping them up into probability. So this is what we're going to use to represent continuous random variables. And we're only going to use two types of density curves. We're going to do uniform density curves, which are rectangles. But really, in most cases, they're just going to be squares. Normal curves, these are normal CDF. So this is a lot of stuff that you have seen before. All right, so here are a couple examples of a uniform density curve. So x is a random variable between 0 and 1. So that's a length of 1, or a base length of 1. It's produced by a random number generator, so it's not just fractions like 1/2, 1/4. It could be irrationals. It could be anything. All right? And so all we need is for this to be an area model. So if the base is 1 and the area is 1, then the height has to be 1. So all you have to do is to take the difference between 0.7 and 0.3, which is 0.4, times 1 is going to give you an area of 0.4. So that's the probability of being between and including 0.3 and 0.7. Now, if you've got an OR statement, that's two things going at once. So x is less than or equal to 0.5. That's going to be shown here from 0 to 0.5 times 1 is an area of 0.5. And x is greater than 0.8. That would be 1 minus 0.8, which would be 0.2 times 1. And that'll give you an area of 0.2. Since they're connected with OR and OR means plus, that total probability will be 0.7. Or you could do 1 minus the clear part, right? That would be 0.8 minus 0.5 is 0.3. 1 minus that again is 0.7. So the only other thing I can tell you is if you have something longer than 1, then make sure that you set the value for the height at whatever it would take for that length times the height to equal 1. But in most cases, we're just going to be working with squares. Now, these do present an interesting thing that is quite a departure from what we're used to with discrete. So you're looking at the same density curve, and half of it's red, half of it's white. We want the probability of the red. And they're giving us a choice of how to say it, like the probability that x is less than 0.5 or the probability that x is less than or equal to 0.5. So which one is it? It really depends on what makes them different, which would be the exact value of 0.5. And if you look at this thing, 0.5 is just that black line that separates the two colors. And if you have an area model here, then you got to ask yourself, what would be the area of that black line? And since lines are only single-dimensional geometric objects, They do have length but no width. So if they have no width, the width is 0, so the area length times width will be, well, whatever, times 0. So there are no point estimates here in continuous random variables. We don't have them. We had them in discrete because all the probability was piled up at the numbers. And the difference between x is less than or equal to, let's say, 5 and x is less than or equal to 5 could be a great difference, right? If you're not going to include the 5, you could be lopping off a great amount of probability. So this is different. All right, so continuous probability distributions assign a probability of 0 to every individual outcome, x equals this or x equals that. Only intervals from low to high have positive probability. Okay, that's different. Don't try to make that one number have probability. It just doesn't. All right, so normal distributions as probability distributions. Those are density curves, so why not? They can describe a random variable, and so we're going to modify our designation for a normal curve. Before, we described it with the capital N for normal, and it was described by two numbers, the center, mean, mu, and the spread, standard deviation, sigma. Now we're going to give it a random variable designation with a letter at the end of the alphabet, capital. So x is approximately normal with parameters mu and sigma. And if what we're going to do involves standardizing, then we're going to convert random variable x into random variable z. And standardizing puts you in another normal curve from this normal curve to this one, only we're going to do some kind of transformation to make the mean 0 and the standard deviation 1. Standard normal curves have a mean at 0 and a standard deviation of 1. All right? So what I want to do is open up your eyes to a little new technique that may help with the standardizing. Some of you may already know it, but I'm going to show the rest of you. All right, this slide is just highlighting, whoops, went right past it, a certain pair of key questions. So we're only going to highlight one of these. If the question states that they want the probability to be within 2 standard deviations, all right, you're just going to take your mean, add and subtract 2 standard deviations. Mark them to either side of the mean, shade them in, and then find the area of that shaded region, right? Because within is another word for between, all right? The other word that's not up here is beyond. And when we get to the example, we'll talk more about that. All right, this example was handed out in class on a separate sheet of paper so kids could write on it. You can find this under reprints in the random variable section on Canvas. So at this point, I'm going to work this separately from the PowerPoint. The only other thing is the homework. It's in your packet. You can find it. So we're going to get out of here, and I need to set up a couple of things. So I'm going to do one of the pauses that I think take forever, but they actually don't. All right, so I'm referring to this page. We're talking about heights of, it says if, there's, you read it 100 times and you don't ever see the typo, but hey, there it is. So the heights of young women closely follow the normal distribution with a mean mu equals 64 inches, standard deviation sigma 2.7 inches, and that's listed here as random variable y. And you can see that, let me get some color here. You can see that because we wrote it out in, the usual notation. So we're going to do 3 things. We're going to determine the probability that a randomly chosen young woman has a height between 68 inches and 70, that she's greater than 73 inches. And then we're going to do some back standardizing on the third one. Okay, so look, what I'm going to do is sort of highlight how this would be best handled on an AP exam. Not like we haven't done it to where it's acceptable, but oftentimes you just kind of want to get away with the least amount you can get away with. So we'll start out with the first one. And if you want to do it the way the AP people like it the best, start out by drawing a curve that matches the situation, all right? And they love it. They love it when you do that. So this is a curve centered at 64, and we're looking for 68 inches up to 70 inches. And let's go ahead and shade this in. And then what they want you to do is to go ahead and just set the thing up. So let's just say the probability, and this is what, 68 is less than y. Remember, it was defined as a y variable. And so y is between 68 and 70 inches. Now, if you put less than or equal to, same thing, as we learned. So then we're going to set it up with the standardizing, at least the setup for it. So this will be the probability, let's see, 68 minus 64, that's x minus mu over sigma, that's 2.7. That's less than z, which is less than 70 minus 64 over 2.7. All right, that's as much as I want to write on this problem. Now before, we would just go ahead and find the two z-scores and throw them into normal CDF. We're going to do this a little bit differently. Okay, so you need your calculator. You need to get it, just hit pause. But I'm going to go on, assuming that you've done your pausing. I'm going to work out of the calculating page on the scratch pad. There's really no reason to open up a bunch of pages. So we'll pick that. And we want to do, just go to normal CDF. So menu, and do not look under statistics, it's under probability. And distributions, and see the normal CDF. Now what I'm going to do is I'm going to not do z-scores. I'm just going to go ahead and put the lowest x value, or y value I guess it is. That would be 68. And then the uppermost one is 70. And then I'm going to use the actual mu in the problem, that's 64. And I'm going to use the standard deviation too, so I'm going to delete the 1 and put in 2.7. And now when I hit OK, it's going to do all of the standardizing for me and give me a probability, a p-value. So hit OK, and that is it, right? 0.0561, and that's your answer, right? So let's go back to here. So this equals 0.0561. That's it. Right? You don't need to go to any great lengths. You don't need to do any more calculations. AP people think this is just fine. Okay? All right, so we'll do the second one. And this one is, what, 73 inches or more? Greater than 73? So we'll draw this out. And here's 64. Now 73 is pretty far out into the tail, so don't expect a big probability for this one. All right? So the probability that y is greater than 73, and let's just write out the standardizing. That way the AP people know you can do it. So the probability that z is greater than 73 minus 64 over 2.7. All right? And we're just going to do that just the way we did it before. And we're going to expect a kind of a small number. So menu, probability, distributions. If you memorize the numbers in front, you can go pretty quickly. All right. Now your low end here is going to be 73. And your high end is infinite. So I don't know, 10,000. All right. It's not really a z-score, but you know, it's just some big number. What was that? 64 and 2.7. And we're all set to hit OK. Whoa, what was that? That's not right. This is live TV, folks. That's weird. Why did it do that? All right, let's try it again. I'm not going anywhere. All right, so probability, distributions, and I can't go back and see what I did, so oh well. Oh, let's see, so 73, that's what it should be, and 10,000. or whatever, some big number. 64 and 2.7, come on, 2.7, and let's hit OK. Let's try it again. All right, 0.000429. That looks more like it, right? So let's put that down here. 0.000429. And that was quick and easy. Now the last one is some back standardizing. So let's go ahead and set up this curve. We're not going to use normal CDF for back standardizing. We're actually going to use x minus mu over sigma equals z. And we'll find the z, we'll know the mean and the sigma, and we're going to get, well, in this case it would be a y. We're going to get the height, all right? So this is the way it splits. You want to be in the lowest 15%. So we're talking about the 0.15 here and the 0.85 on the other end. So we need the z-score right at that cut point. And if you'll recall, that's inverse norm. And that would be whatever you have from left to right up to that cut point. So that would be your 0.15. And we can get that off of your calculator too. All right, so it's right in the same menu. There it is, choice 3, inverse norm. All right, so the area is 0.15. Now I did have students that put in the 64 and the 2.7 and got the right answer, right? That's fine. I've seen the calculator betray me from time to time, so I'm just going to leave it like that, like I'm in a standard normal curve, and it's negative 1.0364. Right, so that will equal, hopefully I remember that, I may have to go back, negative 1.0364, right? So we can just say that y minus 64 over 2.7, that's got to be less than, and if you want to do less than or equal to, it's the same thing, all right? Negative 1.0364, all right? So I don't actually know this number, so I think I'm going to not bore you with me grabbing my calculator, so stand by. Okay, so all I'm going to do here is multiply each side by 2.7 and then add 64, and I'm going to get y is less than or equal to 61.20172. There may be some difference between what you got and what I've got based on the rounding, excuse me. But remember, this is a measurement for height, so this will be, has to have units, so that'll be inches. All right, so that should look very familiar. We've done this before, and we're just doing this within the framework of random variables. So I've got to hit pause again because I have to change my screen up a little bit, so stand by. All right, here we are. This is actually page 11 in your packet, so if you need to hit pause to open it up to there, go for it, or you can just listen to my endearing story about sampling distributions, because that's what we're going to be living off of second semester. In this particular problem we're going to be breaking down, it says, suppose we know that 35%, 0.35, of students at a college applied to another school as well. That's mentioning all students there, so it's like a parameter. That's not from a sample. That's just a known value for a population. It says then, assume that random variable x is approximately normal with a mean of 0.35 and a standard deviation of 0.0123 for the sampling distribution. Okay, that's a new thing right there. Let me tell you what a sampling distribution is. What we're used to, or what we've been doing up to now, is just getting lots of individual measurements and making a distribution out of them. All right, this is not a distribution of individual measurements. In fact, this is a distribution that's made up entirely of sample proportions. Now think about it. If I go to this campus, randomly pick 50 people and ask them had they applied to another school as well, I don't know that I would be guaranteed to get exactly 35% of them say yes. I might get 34%, I might get 38%. Who knows? It's a sample. I've got some variability in there, and so my results are going to vary from sample to sample. And if I could do it to where I got all possible samples of, let's say, size 50, then I could put all of those proportions or probabilities, percentages, maybe that's the best word, put them all in a distribution which would be centered at the same value as the actual number, but it would have a little bit of variation. And since we're going to be using samples to support claims and make estimation, we're going to be working in sampling distributions. So this is a real early introduction. No, it just kind of showed up. So it isn't like it's something that we're going to use like we would next semester, but at least here it is and we can talk about it a little. So what's the probability that in a sample we would obtain between 33% and 37%? All right, so let's do this in the new way. All right, so this is going to be 0.35, and each of these is 2% below. So it'll be 2% below here, that'll be 0.33, and then 2%, sorry about the non-straight lines, that'd be 0.37, and we want what's in between, so we want that. All right, so this is the probability, and let's see, 0.33 would be less than x, which would be less than 0.37. And there's no change. We're just going to do this the way we did the previous ones. Maybe I'll do it the long way. Who knows? All right, so that'll be 0.33 minus 0.35 over 0.0123. That's an easy one to remember. That's less than z, which is less than 0.37 minus 0.35 over 0.0123. And just for grins, I'll do it kind of the old school way. So if you shrink those down to a single number, that'll be the probability of z, let's see, negative 1.626. That'll be less than z, which will be less than positive 1.626, right? And we'll determine that by doing a normal CDF from negative 1.626 up to positive. And you put that in your calculator, and you should get a fairly big number, 0.8961. Almost 90% of your samples would be between those two. And it makes sense because you're right here in the center where the peak is, and most of your area is located there. So that's the old school way. I think we're going to just roll back into the new school way of doing things. All right, so these are actually two problems in the next one. So we're looking at greater than 38%. Right, so there's 0.35, and 0.38 is pretty far up in the tail. So I don't think we're going to get a big probability for that one. And the other one will be less than 0.34, if I remember right. Yep. And that's pretty close to the center. So we're talking about all of this. And that should give us a much bigger probability. All right. So for the first one, the probability that x is greater than 0.38, and I'm just going to show the standardizing, but I'll let the calculator do it. All right, that's the probability that z is greater than 0.38, that's x, minus mu, 0.35, divided by 0.0123. Okay, we can definitely do this on the calculator, why not? So let's go back into menu, probability, distributions, normal CDF, and let's see, on that one, the low end was 0.38. So we'll put that in there, 0.38. And then the upper bound is just some big number, so 1,000, 10,000, whatever. All right, and the mean is 0.35. And the standard deviation, which we can delete that, 0.0123. And let's see if we get it right, or if I have a weird thing happen. Should be okay. All right, 0.007363. That's exactly what it should be. All right, so we'll go back here. And I don't know. I hope you like that. I think it's pretty useful. So 0.007363. So less than 1%. Right? This is the probability for the second one that x is less than 0.34. And so that'll be the probability that z is less than 0.34 minus 0.35 over 0.0123. And I'll just give you this one just to save time, 0.2081. So almost 21% of your area is going to be the proportion that you're looking for. All right? So now, the last two. This we don't have to do any standardizing at all because we want results within 1.5 standard deviations from the mean. Remember the within from the PowerPoint? So if we draw that out as a curve, all right, since 1.5 is a standard deviation, it is a z-score. So we'll just plop positive 1.5 here and negative 1.5 here. And we're just looking for the values in between. And that's quite simply just going to be normal CDF from negative 1.5 to positive 1.5, right? No standardizing required. It's already in a z-score. And again, it's your central value, so that'll be 0.8661. So it's quite a bit of the curve. All right, the last thing we need to go over is getting results beyond 1.75 standard deviations from the mean, okay? Now beyond is different. It's not within. Okay, so here's 0, here's 1.75, here's negative 1.75, and beyond doesn't point between, it points away. So we're talking about that tail, and we're talking about that tail. So I asked people what would be a good way, that's 0, to calculate this. And almost every class, the first thing was we can do 1 minus the probability of what's in the middle. And that's perfect, right? Negative 1.75 to positive 1.75. Perfect option. Another way, somebody said, well, you could just find the probability of the two tails and add them up. And you can do that. But what can you tell me about these two tails, quite apart from how poorly I drew them? Wouldn't they just be a mirror image of each other? I mean, wouldn't they? It's a symmetric curve, so this probability in here should be the same as this probability on the right. So since they're the same, can't you just figure out one of them and just double it? So that would be 2 times the probability of, well, I'll tell you what. We'll just go straight to the normal CDF, okay? So twice normal CDF. And let's do the smaller tail. That would be like negative 1,000 up to negative 1.75. So you could do this top one, or you could do the next one, or you could do twice the other tail. So twice normal CDF. And that would be from 1.75 up to infinity. So we'll just use a big number like 1,000. However you choose to do it, I am fine just as long as you get it right. It won't represent much of the curve. It's 0.0801. All right, that's all of your notes. That's what you missed.